Hello, everyone. Welcome. We are starting now the IEEE CASS Rio Grande do Sul talks promoted by our CASS Rio Grande do Sul chapter. So we are here to watch the talk by Professor Marcelo Johann from Federal University of Rio Grande do Sul in Brazil. He will talk about algorithms for physical design, fundamentals and challenges. So today we are here to attend the talk by Professor Marcelo Johann. So Professor Marcelo Johann is a PhD in computer science from Federal University of Rio Grande do Sul at Porto Alegre. And he was a visit student also in UCLA in 1997. And he also worked as a professor at the Catholic University of Rio Grande do Sul for 2 years, 3 years actually. And then since 2003, he is a professor at the Federal University of Rio Grande do Sul. He co-authored 9 book chapters and published more than 70 conference and journal papers, mainly on topics related to electronic design automation. So his interests are algorithms for placement, routing, discrete gate sizing, combinatorial optimization, circuits for audio recording, classical music, and computer music. So I would like to thank Professor Johann for accepting our invitation. The floor is yours to start our talk today.
Okay, thank you for the introduction, Claudio. Good afternoon, everyone. So, as the title of my talk says, I have been working with algorithms for physical design in the last 30 years, and I want to talk something about fundamentals and also recent challenges or trends in the field, representing not only my personal experience as well as what other people are typically doing in this field. Okay, giving something like a spoiler, one of the lessons that I want to say to you is that this field is very important in our society, because EDA is something that enables the evolution of computer science and all the revolution that this gives to our societies. So I will start by providing some context in this sense, and then we are going to talk about fundamentals of problems and algorithms, how we solve the tasks that we need to design these complex integrated circuits. And I will give some deeper look at the problems that I usually teach and research on, which is placement and routing. Not saying that these are the most important problems to work on, but as you're going to see, at least we need to generate something. So among all the tasks that we need to do, like simulation, representation, verification for designing a successful implementation, we need at least to generate things, and this is a good starting point, at least for beginners, to see what we have to do. Okay, so integrated circuits are everywhere, and anyone today can take one of these small black pieces, burn it, crack it, and look at under a microscope to see the beauty of all these intricate details that our engineering is capable of producing. And of course, this has a role in our entire society today. And it all started many decades ago when we realized that we could implement and fabricate more than a single transistor at the same component. And we started to implement logic functions, operators, memories, entire processors, and at some point, very complex circuits and systems. At some point in this evolution, we start caring about giving names to these scales of integration. So we went from something that could be designed by a single person by hand, and sometimes it was designed by a single person, to systems so complex that they require hundreds of engineers working during many years just to design. And look, this is actually very old. I keep this slide because it has data of how many engineers worked on the design. Today, we are designing chips that have tens of billions of transistors integrated in the same die. And also, among many other facts that we can check in this industry, is there is the cost of fabrication. So the foundries that are needed to fabricate these circuits, they cost up to $10 billion, perhaps more, depending on how recent they are and what are the technologies they are employing. And a set of fabrication masks to design a new circuit is something also that requires many millions of dollars. And so it's not any company that can design such a system. And of course, we need to pay for that, and this must be efficient. It's not a simple thing, this industry. And if you compare to other things that humans have produced, I think there are probably no other products that employ the same number of components inside. There are no cities with billions of roads. There is no house with a billion of components inside. There is no car with a billion of components inside. And all of these integrated circuits, they will end up in the latest cell phone that people are going to use to contemplate cat videos and engage in argument with strangers on the internet. But one thing to understand is that this must have some benefits for us. What enabled this evolution is not only that we know how to do this, because we know how to do in terms of science and practical know-how. We need how to go to the moon 50 years ago. But we stopped going there because we didn't have the same amount, the same size of benefits to our society. And so more than knowing in terms of science and fabrication technology, we have to have this economics, right? We have to have some benefits that everyone wants to get. And that's the case with the cell phones. No matter what people do with them, they want the cell phones. And of course, we have more serious and infrastructure tasks in our society, in the industry, fabrication, medical care, the food chain, that all benefit from the integrated circuit industry. But none of this will be enough if we had to design these chips by hand, because that will be completely impossible. When I showed the data from the cell processor by IBM, you can see that there are that large number of engineers working on the same project, and they were already using EDA tools, so automation tools. And that's kind of show to us that it's completely impossible if we are going to design an integrated circuit with this number of elements today by hand. So my point is that automation is indispensable. It's not only key, but it's indispensable for the integrated circuits industry. And therefore, we need tools to do that. We need not just simple tools that an engineer uses, but we need to automate as much as possible. We need to take the experience of the engineers, what they do, and implement an algorithm that does the same thing. In general, as I was trying to talk at the beginning, we would need many tools that will support this design, and just represent this number of elements and load them and display on the screen is a difficult task, because you cannot write a simple code that reads a file with 50 billion lines, for example. It's a challenge. But among the many tasks and software infrastructure that we need for this, there is this basic synthesis steps, because we have to create things. So we have to start with an algorithm that solves a problem, or this algorithm is itself a processor that will interpret other algorithms. And high-level synthesis will create a machine, an architecture that implements this algorithm. This architecture will be composed by a control part, that determines at each cycle what is going on, which data goes where, and which data is processed by some operator, and the data path, which is the collection of registers, operators, and connections among them. Then there is logic synthesis, which will take this description and it will detail it so that we know each gate that needs to be used. So logic synthesis will perform several optimizations, logical optimizations, and at the end, it needs to map this logic functions as well to the gates that are available at the target technology. For example, in CMOS, we typically use only negated gates because this is easier and shorter function to implement. But on an FPGA, I can implement any function on a lookup table. And last but not least comes the physical synthesis, which is where I have been working in the last decades. So physical synthesis will be concerned with the sizes and the positions and how to interconnect things. Basically, physical dimensions, where things are at the chip level. And it is represented by these two simple problems of placement and routing. But before going into this placement, I would like to give an overview about the nature of the computer problems that we have to deal with and the algorithms or strategies that we have to solve them. But I will take the placement problem as a starting point. So this is a corner of an integrated circuit that was being designed by a student in one practical course several years ago. And we can see the power grid here that goes, and we can see that the cells with the active elements are organized into rows, and there is a routing channel between them. This is a node technology. And these cells were placed there by some method, and we can see that they are at some position, at some relative order. And my question is, why this order and not any other placement? The reason is that if you place them randomly, the needed routing between these nets to complete the connections will be much higher, and I won't be able to route to make all the connections in this available area. And if I optimize it, I place closer cells that are connected closer among themselves, then the needed routing is reduced, and this can be estimated by the half perimeter wire length of the networks, of the connections. But the problem is that if I would like to take a naive approach and check all the possibilities that I have to place these 12 cells, that will amount to almost 480 million possibilities. And this is for a circuit with only 12 cells. And not just that, but this is only for this circuit. If I take another circuit with 12 cells that has a different set of connections, I have different 480 million possibilities. And so this leads us to the classical problem of tractability in computer science, which is what I can actually compute in a reasonable amount of time. And it's related to the classical unproven problem, which is everything that can be verified in polynomial time can also be solved in polynomial time or not. But even though if someone answers this question, there are still problems that are not in the NP class, because NP relates to a non-deterministical polynomial. And there are problems that even if I had a non-deterministical machine, I could not check the validity of a solution in polynomial time. But just to give a real sense of what this is all about, I have 3 simple examples of algorithms, of codes that are in the P class. So all of this is polynomial. And the first one is linear. Then I have some square algorithm. And then I have some that will take a much more time to compute. But everything is in the class P. And here I have the simplest example, probably that is not in the P class. This is a function that computes the factorial, and in fact, it calculates by enumerating. And so the total here will be the factorial number. And it has a number of iterations, and for each iteration, it calls itself recursively. If we test this function, so this is the same function in a C program, and you can see, you can try this at home, and you can see that you get almost instant response for small numbers. But as you pass 10, it starts to get slower. And so for computing the factorial of 13, I call it the function time, and it shows that it needs more than a minute to compute this. And how these functions grow is very radical. And this slide, I reproduced here this important knowledge, which is Coban thesis, that people sometimes forget what's the rationale behind this. The problem is that functions like this one, factorial, is a combinatorial function. It grows so fast that I cannot compute realistically for a number of elements that is quite small. I cannot probably reach 20 in this case. And if I had just to design circuits with 10 transistors or 10 connections or 12 connections, I could do this by hand. I didn't need a computer. We actually need the computer because we are designing circuits with thousands, millions, or billions of components. And that will lead us to this division, this important distinction about polynomial things and not polynomial. So n to the third is actually a slow algorithm, but is actually doable for a quite large number of elements at its inputs. But if I have cells at this area that are painted purple or blue, especially the blue ones, they have some special characteristic. These numbers are larger than the number of atoms in the known universe multiplied by the time, the quantum time since the Big Bang. So this is a guarantee that you are not going to be able to check all these possibilities. And that's what makes polynomial class algorithms so interesting. They are practicable, even though some can be a little bit slower than the others. But if you have something that is exponential, like 2 to the n, or combinatorial, like factorial, then it's almost guaranteed that we are not going to process more than like 15, 18 elements. So we are not going to be able to employ this naive approach for placement or routing or anything else. And that's exactly what I proposed when I look at the placement problem, is that if we have 12 cells and we have to place them, like we have 12 options for the first cell to choose, and from each one I have the 11 other remaining cells to place at the second position, and so on. And so this is the solution space where I have 408 million leaves here. And each one of them will have some quality. It will have some of those pictures of a rat nest of the needed connections, and I will represent the needed connection by a number, which is the sum of the total half perimeter wire length needed to connect them. And not only this space is huge, as I showed you, because it's already big for a simple circuit, but the possibilities of the functions here are very wild. Each problem, placement, routing, legalization, we have a different shape of function here, and I cannot even look at this function because I cannot enumerate all those possibilities, right? So our task in the EDA community, in the EDA field, is how to write software, write algorithms that can find one of the best solutions in a landscape like this, that I'll try to get a sense of how it is along my career, and the algorithm finds a good solution, because you can see that at some place, if I just randomly look at some positions here, I would find a good solution. But in other landscapes, like the lowest two, it's very hard, because I can look and find many solutions, and then there is a very deep file in somewhere, and there is a solution that's much better than what I'm looking at this moment. So our situation so far it looks very bad, because almost all problems are at least incomplete or NP hard, or they are not in NP class. The surface of this CASS function was never seen. It's difficult to have an idea of how it is. And we need to design circuits with not only 12 cells, but 1 billion cells, for example. And also it must be for tomorrow. Of course, the circuits must be designed fast, like for some months now, in a time scale. But there is this known practical rule in the industry, which is the 12-hour rule, because if you let the tool running overnight, the engineer gets the other day and gets the result. Oh, okay, this is the placement I got, this is the routing I got. And if you don't have this, you are going to waste one entire day of the engineer, because it will be sitting there waiting for the tool to end. And this looks pretty scary. But one of the lessons that I want to give in this talk is that this is a radical theoretical view. And in practice, we solve these problems every day, and we do this in almost linear time. We have to do this. We have to find some way in which we program our tool that it solves in linear time. I mean, it takes 1 hour to solve a 1 million gate circuit, and it takes 2 hours to solve a 2 million gate circuit, something like that. As an example, we all have computers with 64-bit multipliers or any other operator. And we cannot represent this table. We do not represent the truth table of one of the outputs of a 64-bit multiplier, because it has 2 operands of 64 bits. And so if we do some simple math here, we can see that we have 2 to the power of 128 inputs, Boolean inputs, and roughly the 2 to the 10 is equal to the 10 to the third. So each 10 at the exponent of 2 is equal to the third 3 exponent of 10. And doing some very rough roundings here, like 2 orders of magnitude, we can see that this is about the square number of atoms in the known universe, which should be quite large. But actually that kept me thinking of how big is this? Is this like a star or like a grain of sand? And so just for fun, I made this graph many years ago. And for my surprise, here is the square number of atoms in the universe, and Earth is bigger than that. So that number is smaller than the Earth. It perhaps is some kilograms or some tons of material. What led me also to the conclusion that if I just associate the number of atoms in universe by size, how many elements I have this scale which gives me complexity, because indeed we need many, many orders of magnitude more elements to create more complex things, like a cell or a living being or a society. And for my surprise, the largest part of the complexity in the universe is below Earth, not above it. But this is just for fun. I digress. Let's go back to the EDA. And so how do we solve these problems in practice? Because I said that engineers solve this every day, this kind of problems. There are 3 main strategies in my point of view, and they are not in any particular order here. So I'll start by looking at the last one. We need better optimization algorithms. And here I will provide just 2 simple examples. One is satisfiability. Satisfiability is almost the definition of an NP complete problem. I have a Boolean formula with a conjunction of disjunctions or a product of sums, and I want to know if there is any assignment of the Boolean variables that leads this function to evaluate to 1. And this, despite the fact that this is a classical NP problem, there are very efficient solvers for satisfiability today. And they can take hundreds of variables, hundreds of clauses, and they allow works like this one presented in ISPD 2019, where I can model routing and several design rules for a cell generation, and I can find the optimal solution using one of the solvers. The other example that I would like to provide is geometric programming, which is not that widely known, because usually people know about linear programming, quadratic programming, things like that. But geometric programming, and there are many other models today besides SAT and GP. Geometric programming can model very strange mathematical functions, such as fractional exponents and something like that. So I can write equations with polynomials that are very complex, and it can solve for hundreds of variables, for perhaps thousands of variables, and find the optimal solution. So one way to take this is this approach. But doing so, I'm insisting in finding the optimal solution. There is, and I will show you that this is not always the best case. There are another possibility, which is restricted cases. A very old example is river routing, or any kind of single layer routing. Here, there is an integrated circuit die, which is part of a TV. It's in the side of the screen. And if you look close, you can see that there is a routing of many connections, because it will take like a number n of wires, and it will decode to the n. And each wire of this will be routed, and there are some bands, and will address one of the columns or lines on the TV screen. And this is a routing that has some particularities. It's a single layer of interconnect, and all of them will be routed in the same order. And this is one classical example of a restricted problem. For each, I will write an algorithm that is much simpler than a generic one that will need to route signals inside the integrated circuits. Okay, another interesting case that I'd like to point to is graph coloring, because graph coloring is also a classical NP-complete problem. But there is, for example, this paper by Olivier Couder, which is exact coloring of real-life graphs is easy. It basically shows that the graphs that happen in real life, for example, the roads of a city or the connections inside an integrated circuit, they are not as arbitrary as they could be. They are not a mass. They are something that has some structure and some limitations in the number of connections. And almost them have one mathematical property. They are one perfect. And so it treats these graphs, and it can solve them optimally in polynomial time. And even the instances that are not one perfect, we can treat them as if they were. And we are going to find a solution. We are going to adapt the solution at the end to increase, to put some additional colors to solve the problems that were left. And in most of the cases, besides the fact that the algorithm is not guaranteeing that it can find the optimal solution, it does find it. So this is one interesting approach that we can perhaps use for other problems, is to treat them as if they have some restriction. And of course, in my personal view, I think the most important thing that we can do is to manage how optimal we want the solution to be. I have two examples here. One is of reordering variables in a binary decision diagram. The BDDs, they can be small or large for the same function, and as a function of the order in which the variables appear in each level of this graph structure. And we can just change the variables that are at neighboring levels. This is an easy operation. And one classical approach that is in the books is to take each variable and scan it, place it on every position, and choose the position where it produces the smaller BTD, and then do it for the other variables. You are using a greedy algorithm. You're not guaranteeing that your result is optimal, but it's a practical one and frequently leads to a good result. There is another paper that I have not described here, but I will point here, and you can look at it. It was recently presented on ISPD, and it does a very clever selection of techniques. You can see, reading the text, that he is always considering this global approach and how many possibilities you have, and what you can enumerate by brute force. What they mean is look at every possible combination in a window to improve the placement, and what they could prune, or in which order they take the decision, so that they get efficiently fast to the solution. So at this time, let's talk a little bit about algorithms for these two selected problems of placement and routing. And I will cover both the fundamentals and some of the recent trends and ideas for improvement. So for placement, one of the classical algorithms that were used in the past was simulated annealing. Simulated annealing is a process that mimics some things that happen in nature, even in stars, which is we have a hot system, and it is being cooled down, and we use this in the metallurgy. We melt metal, and we have a schedule for the temperature, so it gets cooled down a long time. And I can simulate this in the computer. And the idea is that if I model this process, it will find a good arrangement of these particles. And in placement, it will optimize and minimize the routing, the connections. This algorithm is so simple that I can write it in a single page of code. This is a complete placer. It's a simple placer, of course, but it can take the number of elements, the number of connections, the side of the circuit, a list of connections between cells, and it considers all cells with the same side, and it optimizes the position of the cells in a matrix with the side given, and outputs the result. You can look at a better description of this, pointing out which part does what at this set of slides here. And I made this, in fact, to teach, because there is all the details are here, of course. But what simulated annealing does is it make a random perturbation in the system, and then it also selects if this perturbation, if it will be accepted by a random function. It always accepts if it improves the solution, but if it does not improve, it also may accept given a probability that it's proportional to the temperature, inversely proportional to how much worse the cost got. So the beauty of this process is that it doesn't know what is he's doing. It doesn't know any particular knowledge of this problem. It makes a random perturbation, and it randomly accepts it or not. So you can apply this for the largest variety of problems. The main limitation is that it's not very scalable. It is slow because it's random. It's like Brownian motion, for example. And so it's not practical when cost evolution takes time as well. If I needed to do an electrical simulation to see if my design improve or not, for each random perturbation, it would take forever to run. But nevertheless, this was one of the most used placement algorithms in the 80s and 90s. Until analytical placers arrive. So at the beginning of 2000, not only fast place, but a lot of many works that followed this, they found a way to calculate an equilibrium position of all the connections in the circuit in a process that it resembles a Lagrangian relaxation. You make a system of forces, you compute a position of equilibrium, and you ignore the fact that cells get one on the top of each other. So we ignore these constraints, and we are going to refine this process until you remove these overlappings. This is done by a quadratic system of equations whose solution is the solution of the linear system of the derivative. It's independently calculated in x and y. And after you get this first solution where all the cells want to be in the middle on top of each other, you have to have some way of spreading them out. You do this by computing the parts of circuit that are overutilized. And the idea here is that you are going to increase this area and make the cells inside the overutilized bins to go to some place that is a larger area. And the way you do this is that you compute the force that would bring the cell back, and you you insert in the same system a force that is opposite to that counteracts it. And then you run the system again. So you are just changing the forces in the system. You're not making it more complex, and you're running the system again until it optimizes its solution. So, and this is one of the main global level improvements that we have in place. And of course, we have many more detailed techniques that happened in the last 1 or 2 decades. But this is the main overview. And what are the trends today? First, there is this problem of scalability because we have to design blocks with several million gates. And so this is a modern concern, how I can implement my new placer with the latest technology that I developed, and how can I make it run for 5 million cells, 10 million cells, 15 million cells, because this will be needed to design circuits with billions of components. How do I explore parallelism? Because I have clouds and clusters of machines. This is not always a trivial task. For example, simulated annealing is a process that is dependent of the order in which the decisions are taken. It makes just one perturbation in the circuit, not many perturbations. So it's a sequential process. It's not trivial to make it parallel. Also, I have to make the placement routing-driven, timing-driven, power-driven manufacturability. And this is also a challenge. People have tried this many years ago, and the first attempts were not very successful, because when you try to meet several objectives, you probably end up not meeting any of them. And so as a base, people understood that in the global placement step, I want to concentrate only on half perimeter wire length, and I would ignore most of the time other aspects, and then I will start to refine them after that. After I have a good global first solution in terms of needed routing, then I will start to consider other factors. But of course, all modern placements, they consider routability and density models. I have to have limits to how many cells I put at each part of the circuit, because in the design process, in the later steps, engineers will make changes to the design, and I will need to insert buffers. I will need to change a lot of cells, and I need to have spare space to place the cells. So this will provide density models, for example. Also, I have to have predictability and stability for the algorithms. I need to quickly know what my placement will do when I'm doing logic synthesis. I need to quickly know, have a glimpse of what the routing will look like when I'm doing placement. This is predictability. And also, if I do some changes and I run it again, it doesn't matter if it needs to use randomized algorithms inside. It must output a design that is similar to what it did before, so that I can converge in my design process. And finally, in this slide, I will just point you to 2 works. I think the first one by Igor Markov has a more recent update somewhere. But these are 2 good pointers for someone that is interested in trends, recent activities in placement, because they give what has been done up to this time, and what are the hot problems that this field has to deal with. And let me start by talking a little bit about routing. So the maze router is the most important algorithm you need to know if you are going to start in this field. It's a point-to-point shortest path connection method. In fact, the term maze router is an adaptation for a grid of a path search graph algorithm in which you have the same costs for each neighbor, for each step. So I'll go from a search to a target, and I scan the neighbors. I will like generate neighbors for each cell that I have in an open list, and I will do this recursively until I find a target. And when I'm doing this, I'm going to put a label that can indicate the order of sequence, as in this slide, or I will record a pointer to where I came from. Either way, I will be encoding the information of all the paths that start from that source until I reach the target. I won't go into detail, but I have this code that you can compile and run. It generates a picture like the one that is on the slides. But you can see that it's a very simple algorithm. I have a queue, and I will push source at the beginning, and for the algorithm enters a loop when it takes nodes from this queue, and it generates the neighbors. And of course, if it checks if the node is still available and if it reached the target, the destination. This is very simple to implement, and it works because this queue is able to represent the nodes that are closer to the beginning, provided that we have the same cost for each move. If you have additional costs that can represent congestion or different RC characteristics, then you have to use a priority queue in place of the queue. Okay, when you do the backtrack here, we will need more information, but the idea is that you can use this encoded information to find a path from the target to the source back. To do this, we need to store pointers at least in this process, and you need to separate what is taken and what is a pointer. But the main problem of this process is that what I'm describing is only able to find a single connection. And if I have another connection, the connection that I made first might make this other one much more difficult. And if I took this second connection and make it first, of course, that I have a better global solution. But then if I have another connection, and so I think you can see the picture. It's dependent on the ordering of the connections. And this is combinatorial. So it's an algorithm that's only good for a single connection. Okay, in terms of the speed, it can be much improved by the use of the A-star algorithm. The A-star, known as heuristic search, is an algorithm developed for in the artificial intelligence field, and it employs an estimation of the path that I have still to go. So in this place, in this case, I start with the number 10 because I need to go at least 10 to reach the target. And so I start to scan around and mark everything with 10 because I still have some path that I went and some that is remaining, and the both add up to 10. Until I realize that it's impossible to reach the target with 10 steps. Then I'll start to search things that I can reach with 12 moves. And so until I find this solution. And for this, I saved a lot of effort compared to maze router. And this is just, it's not just a little, it's really a lot. Imagine that I have different cost regimes and I have a 3D grid with many routing layers. The A-star algorithm will be much, much faster. So in a nutshell, the maze router has these nice properties. It always finds a path if there is one, and the path it can find is the shortest possible. But these two advantages, actually in practice, they might be problems. The fact that it always finds a path, it means that if there is some tricky path that go around all the circuit to connect to points, it will go to use that path, to propose, and the tool will use that path. And so it will waste a lot of resources to kind of solve one problem and ignoring that this is not solving anything if there will be many other connections that need those resources. Um, and also, as I said at the beginning, we need to sometimes forget that we have some optimal solution. Maybe there is another path that is not the shortest possible, but it's much straight. It's a much straighter path, and it will save vias. It will be more reliable, and so on. But on the other hand, maze routers were sometimes avoided because they have the problems of memory, speed, and ordering. But today we know how to solve these problems. We have plenty of memory in general, and the speed would be slow if I had to model every single position of a grid in memory. But I don't need to do that. The beauty of the maze router or path search in general is that it can run on any kind of graph. For example, I can, on an FPGA, I can scan looking from track to track that are already implemented on the page of PH. So when I go from one pin to one track, I'm not only at this XY position, but I am at the whole track from one side to the other side of the circuit. I can use Hanon grids, and of course, as I show, I can use A star to improve speed. In the ordering, I will not go into detail here, but it can be dealt with by negotiation, which is a kind of Lagrangian relaxation process. I will let all the connections to use the same resource, and then I will evaluate the demand for this resource and increase the cost of it so that the connections that have options, they avoid to use this resource. So what are the takeaways from maze router? It's still the most important, the most used routing algorithm. Probably modern routers are employing a set of different algorithms, and at some step, at the beginning or at the end, they use a maze router to make some of the connections. One example of how different effects can be achieved by a process like this is this paper that we published many years ago, that it can build different standard tree structures with different performance trade-offs in terms of delay and the size of the tree by using maze routing, or specifically A star. So what are the routing trends that people usually talk about lately? First, you have to have a maze router or an A star based router as a base algorithm on your router, or a cleanup. If all other methods fail, you call the maze router to complete the connections, because it's much more capable than the other methods. Also, pattern routing is a hot topic. Pattern routing is try to connect your points by straight lines, by an L shape, one side of the other, or a Z shape. And so you have a small set of patterns. You just have 1, 4, 1, 4, 1, 4, and you try to connect that way. You are going to solve probably 80% of the connections in a circuit with very simple paths, and wasting a very small amount of time. Also, we can model small parts of the routing problem as SAT problems, as mule routing, and so on. Trunk routing is another topic in which, instead of looking at each terminal, I look at the whole disposition of the terminals that I need to connect for a net that has more terminals. And I place one single trunk, a large track that that covers most of this region. And then I connect all the terminals to this trunk. There is also problems specifically to analog circuits like length matching routing and so on, and many different classes of problems like tree topologies, buffer insertion, obstacle avoidance algorithms. And one thing that is interesting is that this area you can have many dedicated algorithms for each problem, unlike placement, in which you are going to use more generic problems. So, to conclude this talk, first, in my experience, the most important things when we are studying and we are selecting these algorithms or we are implementing some tool is how we are going to manage complexity versus speed in terms of the understanding the algorithms. Because, for example, if I'm going to make standard trees, so how large are these trees? How many gates I can drive with a single output of CMOS gate? Probably not many. So there are just a few trees in the circuit that have fan out more than like a dozen. And so should I care about complexity or not? Should I make the same algorithm for all this signal nets, or I will say, let me have this code for nets up to 10 terminals, and then this other code in which I care a lot about complexity, how it increases with the number of terminals for nets that have a large number of terminals. If you think pattern routing is something like this, is to write a simple algorithm for just two point-to-point nets that have only two terminals. Also, we have to manage this idea of am I going to look for the optimal solution or not, or just good or not? I can make several simplifications in many algorithms that make them lose the optimality result, but they may actually being output the optimal solution or something very close within 1% or 2%. I have to access this and manage this when I'm selecting the algorithms. And something more important here, I have to manage specialization versus generalization. I have to decide if I already gave examples of that, if I'm going to make an algorithm that solves all the problems, or I will select a collection of algorithms, some which will be specialized at some parts of my circuit or some nets with some characteristics and so on. Okay, also, you have to try to use priorities together with heuristic. If you have a heuristic, it may be very bad because it may be stuck in a local minima and find a bad solution. But if you have the right selection of priorities, this is indispensable, this is more important than that, and then you place things greedily, but in this order, you may actually find a very good solution. Other different ideas that I observed a long time, you have sometimes to randomize your code and to apply some kind of jittering. For example, if you take the code I have here in the slides on the I star, it will insert the nodes always in the same order, the neighbors, and it will end doing the connections always to the same side. And I can randomize that order and make the connections more distributed in the chip. And this is not that many, is not much used in this field. Also, we can use not only dedicated algorithms together, but we can publish papers that don't need to win in every situation. If I have a fast algorithm for something that have 10 elements or 12 elements, I can use together with other algorithms that are in other papers if my algorithm finds a better solution for some of the instance. Maybe in average it loses, but it finds some solutions that other algorithms are not finding. So I can add this algorithm to a set, and I can employ this in a tool, try the solution by this method, take the best. This can be very effective. And so my final thoughts here are the following. First, EDA is fundamental. That I said since the beginning. Most is not optional, and that's the key for us to understand how we are going to solve this quickly. We have to pay attention to some numbers because they are very important. If the net has 10 terminals or 100 terminals or 50 terminals, and how my algorithm will behave with that particular number. And as always in the last years, I observed some people that moved to other problems saying, oh, okay, for example, this problem was already solved some years ago. Is there room for improvement or not? or not. And I would ask everyone to check what was our understanding of placement, routing, legalization, uh, maybe 10 years ago or 15 years ago, and compare to what we know today. And we are going to realize that we know much more today than we did in the past. And so that same thing is expected to happen in the future. Probably someone talking like 20 years from now will teach you things that are much more effective and interesting than what I'm saying today. So there is always a lot of room for improvement, and there is this need to design circuits with an ever increasing number of elements. And for that, in my personal view, at least until artificial intelligence can design everything for us, which is something that is probably going to happen in 20, 30 years, at least for that, we need better people with a good, not better people, but people with a strong background, both in computer science and in engineering, in circuits. So we need engineers that understand the complexity very well and were trained with the best methods, mathematical methods and computational methods and data structures that we have to deal with this the size of these problems. And also we need computer scientists that are not afraid of hardware, that have a strong background on circuits and systems. And so that's the lessons I want to share with you today. And of course, I'm available for questions if I can answer some of your curiosities or concerns.
Okay, thank you, Professor Marcelo Johann, for the very nice talk. There's a question actually by Professor Altamiro Suzin. Here. Nice presentation, thanks. My question is about the number of layers. It seems that it is not so important. How do you decide to jump to another layer?
Well, that's a complex issue. In fact, I have many routing layers, even though some are reserved for global connections like power lines, even some might be reserved for clock. And the bottom layers are for connections inside the cells. Even though I have reserved layers, I'm going to perform the signal routing of the chips employing like 4, 6 layers, 6 metal layers, perhaps more. Another thing that might limit this number is the fact that I'm going to have different teams design different parts of the system. But nevertheless, we have routing in many layers. This is not that much difficult for the detailed router. I think it's more a question for the global routing, which I not addressed here in this talk. The global routing is the step responsible for distributing the connections among the circuit. And he might also be the one that is responsible for assigning the connections to specific layers. There are 2 known models. In one, the global routing only sees the circuit as a 2-dimensional grid, and it says in which part of the circuit each net will be routed by the detailed route. In the 3D model, the global routing, it's an abstraction in X and Y, but it's detailed in the Z in the layer axis. So it assigns, and it has to assign the interconnects to particular layers. And so it's not that it's not important, it's not a concern, it's just I did not address this here. And it's among the basic and dedicated advanced algorithms. Every algorithm can be adapted to that, but it's another problem. It's another step to be done. It's like placement. I just talk about placement, but there is the global placement, detailed placement, legalization, and so on.
Okay, nice. Please feel free to address your questions in the chat that we're going to addressed to the speaker here. So I have a question, Professor Johan. It is about many companies, EDA companies. Are they have they are not opening the source code, right? So we don't know which algorithms, which physical design algorithms are there. And now we are looking at some movement to open source EDA tools. So this is going to, with the open source community contributing to these algorithms, do you think this is going to be uh, like improving the algorithms that we have now for the commercial tools?
Um, I think yes. It's a complex question, but I think yes, it will contribute in the same way that Linux contributed to the operating systems development. We cannot blame private companies for protecting the intellectual properties. But we need to understand, and they also understand, that this it turns it hard for people to research and to understand what's going on if they don't have access of this information, if they are not able to compare the results because of NDAs. And so even the private companies, they make an effort to be as open as they can. And I think this recent efforts in making open source EDA is very valuable. So I think it will help improve the EDAs too, the commercial tools, and I have no doubt that this is important. I think
Okay,
that's
nice.
my answer.
We have another question here from Abhinandana Reddy. In placement stage, why we are deleting clock buffers and adding?
I'm not sure I understood the question about deleting clock buffers, but the clock networks uh, are a universe apart. I have to have special algorithms to design, to place, to route the clock networks. Even the structure of the clock is different. And so I think I didn't get exactly the question about deleting and inserting. Anything can be done or changed as ECO to improve the design. If something is slower, I will perhaps place a buffer to turn it faster. If something is fast enough, I can, for example, delete a buffer to make that part of the tree slower. I don't see the placement algorithm doing this, but the clock routing or the timing algorithm doing this. So the placement must be able to do this if the time closure needs to.
Okay, I don't get if this is a complement of the question of another question, but why flops is used in design without flops fast design right? And then he complements with flops increase the propagation
Okay,
delay.
I think this is more of a philosophical question. The flip-flops implement time barrier, which is one of the principles for achieving discrete time. Our circuits are digital in the levels which they represent, and they are digital in time, in steps. To create this abstraction of one step, the next step, the next step, I need to have the timing barrier, which is implemented by the flip-flop, which means that I have a timing reference and everything is computed from that moment, and everything is stops to run until the next clock border. And so it's an abstraction that I create for my benefit. But of course, there is a trade-off between the clock cycle and how much I have to compute in each cycle. I can have a smaller clock and compute a few things, which is what the question seems to be concerned with, and I might have a large clock and more things computed at the same period. It will be a trade-off. It's hard to find out the right clock cycle.
Yeah, it's more like a it's not directly connected to physical design, but actually a more logical and high level synthesis problem, like, right? So this is how many flops are you going to put in the to create the barriers. So, yeah. Okay, I think we don't have more questions, so I would like to thank again Professor Johann for the nice talk. And I don't know if you want to say something to the audience.
Oh, just thank you for the attendance. Thank you, Claudio, and
Okay.
Ricardo Reis, and the name of the IEEE CASS Society for inviting me.
Okay. Thank you.